This tutorial demonstrates the use of the DC System Analysis module in the SKM Power Tools software. This module can be used to analyze DC power distribution systems, including those supplied by batteries, rectifiers, and generators. The batteries can be either lead-acid or nickel-cadmium. This tutorial starts with an introduction to the 4 types of studies that can be performed by the DC System Analysis module. The tutorial will continue with the development of a model for a simplified battery-backed distribution system. We will then demonstrate each of the 4 types of studies, including battery sizing, load flow, and 2 methods of calculating short-circuit current. The tutorial will continue with the development of a model for a system supplied by generators and rectifiers and having loads such as trains and large motors. We will also discuss some of the data that is unique to generators, rectifiers, and trains. The tutorial will conclude with a demonstration of adding a new battery characteristic to the PTW library. This will cover both lead-acid and nickel-cadmium batteries. The DC System Analysis modules include battery sizing calculations for both lead-acid and nickel-cadmium batteries, time-dependent load flow and voltage drop calculations, and short-circuit calculations using either the ANSI or IEC methodologies. The battery sizing module is used to determine the size of a new battery for a DC system that needs battery backup. The sizing analysis can also be used to check if an existing battery is adequate after changes have been made to the system loads. A battery sizing study requires the size, type, and time dependence of each load. A sizing study also requires upper and lower limits for the system voltage. In addition, the battery cell discharge characteristic is required. Battery discharge characteristics are stored in the PTW library, and characteristics for battery types not included in the library can be added by the user. The addition of battery characteristics by the user will be discussed at the end of the tutorial. Battery derating factors for age, temperature, and design margin must also be specified. The system connections are usually defined when building a system model, but are not required for a battery sizing study. The setup for the battery sizing study provides 2 options. The size, type, and duration of a random load can be defined. The load size can be specified in amps, watts, kilowatts, or ohms. The load type can be selected to be constant kW, constant current, or constant resistance. The duration of the load is specified in minutes. The second option determines whether the resistance of the system cabling is to be doubled to account for the resistance of the return current path. Typically, the system model is defined with the actual length of the conductors between buses. Since the current in DC systems must flow in both the positive and negative conductors, the total resistance of the conductors is twice that of one conductor. The result of a battery sizing study is the battery sizing report. PTW provides reports that match the sizing worksheets defined in IEEE 485 for lead-acid batteries and the worksheet in IEEE 1115 for nickel-cadmium batteries. Shown here is the beginning and end of a typical sizing report for a lead-acid battery. The report for a nickel-cadmium battery is similar, except the size is calculated in ampere hours rather than in positive plates. For a lead-acid battery, as shown, the required number of positive plates is calculated for each time period. The capacity for the random load is then added to the number of positive plates required for the limiting period. This uncorrected size is then multiplied by the temperature correction factor, the aging factor, and the design margin factor. And finally, the resulting corrected size is rounded up to the next whole number to define the minimum number of positive plates needed for the system's load profile. The load flow analysis is used to determine the voltage at the terminals of each important load device throughout the duration of the duty cycle. The resulting voltage values can be compared to the rated voltage range for each load device. If the voltage is outside the rated range, either the system design or the component can be changed. The load flow analysis is also used to determine the time-dependent current in system cables and distribution components. These current values can be used to determine whether the cables and components are adequately sized. A load flow study requires generally the same data as required for battery sizing. The critical inputs are the load sizes, types, and time dependence, along with the system cabling and connections. The load flow also needs the battery characteristics and size if the system is supplied by a battery. If the system is supplied by generators and/or rectifiers, the ratings of these components are also required. The setup for the DC load flow study provides several options. The most important option is the duration of the time step. The choice depends on the needs of a particular study. For a system with loads that change over a period of several hours, it may be appropriate to use a time step such as 10 minutes. Conversely, if the important part of the study is the few seconds needed for backup generation to be started and loaded, the appropriate time step duration may be 1/100th of a minute or 0.01. The total simulation time normally will correspond to the period of time for which the load data has been defined. The bus and branch voltage drop limits are used in the load flow report to identify buses and cables that have excessive voltage drop. The maximum number of iterations and the mismatch voltage normally can be left at default values, but may be adjusted for a marginally unstable system. The default for the last option is to use twice the resistance defined for each cable in the system model. Recognizing that it's normal practice to define the resistance of a cable as the resistance of one conductor, this option allows the analysis to include the resistance of the return conductor without using an unusual definition for the resistance of each cable. The load flow report has 3 parts for each time period or time step. This slide shows the source summary for the period starting at 2 minutes. This slide shows the next part of the report, which provides detailed information for each bus and cable in the DC distribution system. Again, this is for the period starting at 2 minutes. This slide shows the third part of the report for the period starting at 2 minutes. This part provides a summary of the results for each bus and branch of the DC distribution system. These same 3 parts of the report are repeated for each time period. The results of the load flow analysis can also be plotted. This example shows the time-dependent voltage at the battery terminals. The user selects whether to plot voltage, current, and/or power. The plot can present one bus or cable or several on the same plot. The ANSI short circuit study is used to determine the maximum short circuit current which each bus and/or protective device must be able to withstand. The short circuit analysis also determines the time constant and rate of rise of the short circuit current. This information may be needed to assure that protective devices are adequately rated. A short circuit study using the ANSI methodology requires data to define the short circuit characteristics of the sources. This data includes information to define the internal resistance, inductance, and voltage of each source device. The data is tailored to each type of source device. A short circuit study also requires the definition of the system cabling and connections. The setup for the ANSI short circuit study provides 5 options. You can select to report a fault at all buses or fault only a selected set of buses. Since the short circuit current for only one bus can be shown on a plot, you may select the bus to display. The default for the pre-fault voltage is to use the results from the last load flow voltage calculation. The other option is to use a fixed 1 per unit source voltage. The default short circuit current report lists the currents flowing into each faulted bus one branch away from the fault. If needed, the report can be expanded to list the current flowing in all system branches for each faulted bus. As discussed in the description of the load flow options, the default setup uses twice the resistance defined for each cable in the system model. The results of a short circuit study are given in a report. This is an example of the results for a fault on a specific bus using the ANSI methodology. A summary showing the peak current for each bus is also provided at the end of the short circuit report. The results of a short circuit study can also be plotted. This is an example showing the total current available for a fault on DC bus 2 and the two contributing sources. The IEC short circuit study has the same function as the ANSI short circuit study, but can be used when the IEC standards apply to the system being analyzed. A short circuit study using the IEC methodology requires the same type of data as a study using the ANSI method. However, the IEC methodology is somewhat more detailed and therefore requires additional information and uses different terms than does ANSI. The setup for the IEC short circuit study provides the same 5 options as described for the ANSI study. The results of a short circuit study are given in a report. This is an example of the results for a fault in one specific bus using the IEC methodology. A summary showing the peak current for each bus is provided at the end of the short circuit report. The results of a short circuit study can again be plotted. This example shows the total current available for a fault on DC bus 2 and the two contributing sources. To illustrate performing DC analysis, we need to build an example DC distribution system. Let's start with a simple system supplied by a battery and having a couple of loads, including an inverter. Similar to the analysis of AC systems, we start by clicking on Project, New, and entering a new project name. We can resize the windows and change the zoom with the scroll wheel on the mouse. To define a DC system, it is necessary to display the DC Components toolbar. If the toolbar is not visible, you can use the View Toolbar option to turn it on. DC components typically include buses, cables, loads, and power sources. The power source can be a battery, as we'll use in this example. Other available power source models are rectifiers and generators. One system can have several power sources. We'll start by adding 5 DC buses. We'll then connect the buses with DC cables. We'll next add a DC motor and a general DC load, and feed the system with a new battery. A DC system can also supply AC loads through an inverter. For our example, we'll add an inverter with 2 loads. After completing the DC side of the inverter, we add an AC bus, and a general DC load. We'll next add a DC motor and a general DC load, and feed the system with a new battery. A DC system can also supply AC loads through an inverter. For our example, we'll add an inverter with 2 loads. an AC cable, an AC load bus, and an AC load. To add the second AC load bus, we simply select the first group and use the component clone function. Next, we define the characteristics of each component. To enter component data, we double-click on the component or open the component editor. It is generally best to define the component ratings, starting with the buses. We'll select DC bus 1 and enter 125 volts as the nominal system voltage. When nominal voltage is defined for one bus, PTW would transfer it to the other buses that are connected to it via cables. The minimum data required for each DC cable includes the rated voltage, the cable length, and the resistance and inductance of the cable per unit length of 1,000 feet or meters. Note that the rated voltage for the cable was automatically transferred from the bus rated voltage. For our example, we'll enter 50 feet for the cable length, 0.08 ohms per 1,000 feet, and 0.035 millihenries per 1,000 feet for the cable impedance. We won't show the entries, but the data for the other cables use the same voltage, resistance, and inductance. The length used in this example for the other cables are 50 feet for cable 2, 100 feet for cable 3 and 4, and 200 feet for cable 5. When entering data for several cables that are similar, don't forget to use the component copy data and paste data to simplify your data entry. Next, we'll define the data for the AC buses and cables supplied by the inverter. The data required for an AC bus is the nominal line-to-line system voltage. Select bus 1 and enter 208 as the nominal system voltage. Use the equivalent three-phase line-to-line voltage even if the AC system is single-phase. For AC cables, the user must specify the length and impedance or select the size and type of cable from the library. For our example, we'll enter 100 feet for the cable length and select a cable from the library in size 4. Again, we won't show the entries for the other AC cables, but they'll use the same voltage and library reference, and the size for cable 2 is 8 AWG and the length is 100 feet. The completed entry for cable 2 is shown here. Now that the characteristics of buses and cables have been established, we will define the loads starting with the general DC load on bus DC 5. For a DC load, we start by specifying the rated voltage, which is often different from the system nominal voltage. For our example, we'll enter 120 volts for the rated voltage. The size, type, and duration of the load must also be defined. Here we've entered 120 amp constant impedance load for a duration of 1 minute. We further define the load by adding 60 amps of constant impedance for 59 minutes, followed by 90 amps constant impedance load for 1 minute, and again 60 amps of constant impedance load for 59 minutes. Clicking on the Load Duration Curve button will display a graph of the load versus time. A DC motor requires information similar to the DC load. Here we've entered 120 volts for the rated voltage and 0 kW constant impedance for 2 minutes. As shown in this example, it is acceptable to specify a load of 0 for a period of time in order to model a motor that does not start at the beginning of the scenario. We further define the motor load by entering 477 amps of constant impedance load for 5 seconds, followed by 159 amps of constant current load for 5 minutes. This represents the motor starting after 2 minutes, has a brief startup period, followed by a constant current running phase. Next, we'll define the inverter. We need to specify the rated voltage on the DC side of the inverter. The voltage for the AC side of the inverter is copied by PTW from the nominal voltage of the bus to which the inverter is connected. We'll use 125 volts as the rated voltage, 40 kW as the rated kW, and 350 for the maximum current. The efficiency should be consistent with the expected load of the inverter. We'll use 0.95 for our example. For AC loads, the minimum data required includes the rated size, power factor, and rated voltage. For AC load 1, we'll enter 24 kVA as the rated size, 0.8 for the rated power factor, and 208 for the rated voltage. The time dependence of the AC loads will be defined later when we set up for the battery sizing and load flow analysis. Continuing with our example, we'll select load 2 and enter 12 kVA as the rated size. The final component that we need to define is the battery that supplies our system. The battery characteristics are obtained by clicking on the Library button and selecting one of the batteries defined in the library. For our example, we'll select a lead-acid Gu31 battery. After selecting the battery characteristic from the library, we must enter the rated voltage. The fields for number of positive plates, the number of cells, and the minimum voltage per cell will be adjusted by PTW during the battery sizing analysis. The first analysis we will perform is the battery sizing analysis. The basic system data, including the load profiles and the system connections, are applicable to battery sizing. Therefore, we only need to go to the sizing subview for the battery in the component editor and enter the required sizing criteria. You can select any one of 3 sizing characteristics from the pull-down box at the top. We are going to accept the default characteristics of the RT curve that will give a size in a number of positive plates. Next, we need to define the acceptable maximum and minimum system voltages, the design margin, and the aging factor. For our example, we'll enter 136 as the maximum system voltage and 105 as the minimum system voltage. Based on IEEE standard 485, it is prudent to add 10 or 15% to the cell size for unforeseen loads or less than optimum conditions. This is done by entering a design margin value such as 1.15. The minimum temperature at which the battery must provide the design capacity must also be specified. This temperature can be degrees Fahrenheit or degrees centigrade. For this example, we'll use 60 degrees Fahrenheit. The aging factor is the reciprocal of the capacity at the end of life. Most lead-acid batteries are considered to have reached end of life when the capacity has decreased to 80% of the rated value. For this example, we will enter 1.25 as the aging factor. To run the battery sizing analysis, click on the DC icon or select Run DC System Analysis. We create a new plot with a default name by clicking on the New button. Our next step is to define the time dependence of the loads on the inverter. To do this, expand the study folder, right-click on the battery sizing in the study list, and select AC Emergency Loads. We first select the AC loads, for our example, we'll define load 1 as operating from 1 to 3 minutes, and load 2 as operating from 2 to 15 minutes. In the Study Setup dialog, we can define random load on the system. For our example, we'll add a random load of 10 amperes for 2 minutes. To run the battery sizing analysis, we select Battery Sizing and click on the Run button. A dialog box will appear with a summary of the AC emergency loads. We will accept the data as presented and click OK to continue. PTW displays the Study Messages box for the battery sizing study. If everything has gone correctly, there will be no errors or warnings reported. We can close the dialog and click on the Report button at the bottom of the analysis window. The battery sizing report is displayed in a format consistent with the worksheet defined in IEEE 485. If we scroll to the bottom, we see that a battery with 12 positive plates is required for the system loading we have defined. If you want to print the battery sizing report, select Document Report. This opens a dialog box with a list of all of the currently available reports. Note that there are 2 battery sizing reports listed. One is the classical format defined in IEEE 485. The New Style report provides an alternative format that is somewhat easier to read. We can double-click one of the reports to open. You can print or preview the report from the Document menu. If we return to the component editor, we can see that the battery size is now 12 positive plates based on the sizing analysis. The sizing analysis has also determined that we need 58 cells and a minimum of 1.81 volts per cell to meet the criteria of a maximum system voltage of 136 volts and a minimum system voltage of 105 volts. If we return to the component editor, we can see that the battery size is now 12 positive plates based on the sizing analysis. The sizing analysis has also determined that we need 58 cells and a minimum of 1.81 volts per cell to meet the criteria of a maximum system voltage of 136 volts and a minimum system voltage of 105 volts. PTW determines the number of cells by dividing the maximum system voltage of 136 by the cell voltage required for charging as recorded in the library characteristic. In our case, this charging voltage is 2.33 volts per cell. 136 divided by 2.33 is 58.37, which rounded down is 58 cells. PTW determines the minimum voltage per cell by dividing the minimum system voltage of 105 by the number of cells. Now that the battery sizing is complete, we can run a load flow study. Unlike AC systems, DC load flows need to be time-dependent for systems supplied by a battery. Since we have already defined time-dependent loading and the battery size, we have all the data we need to proceed. To begin, we click on the DC icon, the Load Flow Study option. If we click our right mouse button on the Load Flow Study option, we can select components. The components we select will be available for display on the plots. For our example, we'll select DC bus 1, and for branches, we'll select cables 1, 3, 4, and 5. After selecting components, we click on OK to close the window, and the selected components for display appear under the load flow option. In preparation for the load flow study, we click on the Setup button to check the load flow options. The maximum number of iterations and the mismatch voltage tolerance are iterative solution variables that are only changed under rare conditions where a marginal system has difficulty converging on a solution. The bus voltage drop and branch voltage drop limits are used to highlight buses and branches in the report that exceed the specified limits. For our example, we'll change the branch voltage drop limit to 1%, whereby branches with more than 1% voltage drop will be highlighted in the report. The most important option is the duration of the time step. The choice depends on the need of a particular study. For a system with loads that change over a period of several hours, it may be appropriate to use a time step such as 10 minutes. Conversely, if the important part of the study is the few seconds needed for backup generation to be started and loaded, the appropriate time step duration may be 0.01 minute. For our example, a time step of 1 minute is appropriate. The total simulation time normally will correspond to the time period for which the load data has been defined. As a starting point for this example, we'll use 150 minutes. The default for the last option is to use twice the resistance defined for each cable in the system model. Recognizing that it is normal practice to define the resistance of a cable as the resistance of one conductor, this option allows the analysis to include the resistance of the return conductor without using an unusual definition for the resistance of each cable. Thus, we are going to accept the default of doubling the resistance. When the load flow study options are complete, we click the OK button to continue. To run the load flow study, make sure the load flow option is selected, then click the Run button. As with the battery sizing study, we are presented with the summary of the AC emergency loads, and again we will accept them as presented. As the load flow runs, the study messages appear. Note that the analysis has been performed at 1-minute intervals for a total of 150 minutes based on our study options. Since no errors are reported, we will close the message window and view the results. First, let's look at the voltage on bus 1. The result is a plot of voltage versus time for 150 minutes for bus 1. Bus 1 is connected directly to the battery terminals, so this is the voltage at the battery terminals. For documentation, it is useful to assign meaningful titles to the plots. If we click on the Plot button, we can enter battery, voltage. Click New, which generates a new plot called battery voltage. Next, let's look at some current values. We start by clicking on the plot button. Let's call the plot load flow current. We click New to create a new plot called load flow current. We first click the checkbox for DC cable 1 in the current flow column. This plots the battery current. Now let's look at the current into the inverter so we can see the effect of the load changes with time. We first click on the checkbox for cable 1 to turn off the battery current plot. Then we check the checkbox for current in cable 5. As you can see, the load changes as the AC emergency loads 1 and 2 turn on and off. Let's add the other load currents by clicking on cable 3 and 4. We now have a plot of the current over time in each of the 3 cables feeding our 3 loads. To print this graph, you can click on the Print button or use the Document, Print, or Print Preview. To print in landscape, we'll use the Print Setup to select the landscape orientation. We can then use the Document, Print Preview to see our results. There is also a load flow report, which can be viewed by selecting the Report button at the bottom of the analysis window. Having completed battery sizing and a load flow study, this is a good point to perform a short circuit analysis. We'll start with a demonstration of the ANSI short circuit study. Before we can perform this study, some additional data is needed. Let's start with the battery and the short circuit subview in the component editor. The first field is a pull-down menu that permits selection of 4 different methods for defining the short circuit current of the battery. We're going to use the default 8-hour rating. To compute the 8-hour current rating, we use the published per plate rating, which is 225 amp hours. To convert, we need to divide 225 by 8 hours and multiply by 12 plates. The result is 338 amperes for the 8-hour ampere rating for a battery cell with 12 plates. The circuit resistance and circuit inductance fields apply to any cabling that is part of the battery. For this example, we'll use 0.005 ohms and 0.0001 millihenries. The cell interconnect resistance and inductance applies to the actual battery cells in the battery rack. For this example, we'll use a resistance and inductance of 0.0004 ohms and 0.004 millihenries. Next, we need to enter data in the short circuit subview for the DC motor. The rated size of our motor is 20 horsepower. The efficiency is 0.87 or 87%, and the rated speed is 2500 RPM. For our example, the motor data sheet indicates that the per unit resistance is 0.03 and the motor armature inductance is 0.49 millihenries. We leave the circuit resistance and circuit inductance values at 0 for simplicity, recognizing we have defined a specific cable between the bus and the motor. We now have the data we need for the ANSI short circuit analysis, so we return to the DC System Analysis window. We first select the ANSI short circuit study option, and then click the Setup button. We then select the ANSI short circuit tab. We'll accept the default options, including faulting all buses, using the load flow results as the pre-fault voltage, reporting the current 1 branch away from each fault location, and using twice the cable resistance. We do need to select a DC bus to plot. We click on the Select button. For this example, we'll select DC bus 2. Then click OK to continue. Note that DC bus 2 is now shown under the short circuit study. To add other components to plot, we click our right mouse button on short circuit, select components. For sources, we can plot the battery. Under motor, we can plot the DC motor. All three components now show up under the short circuit study. We can now run the short circuit study by clicking on Run. Again, PTW displays the emergency load summary. We click OK to continue. Study messages are shown during the solution. Since we don't have any errors or warnings, we can close the message dialog. We can now plot the results. We click on the Plot button. We can create a new plot. We'll call it DC2. We can plot the short circuit current at bus 2, out from the battery, and out from the DC motor. As with the other studies, we can bring up a detailed report by clicking on the Report button. The top of the report is a record of the sources of fault current and a table of the pre-fault voltages. If we scroll down the report, the next part of the report, we see a maximum fault current at bus 2, the rate of rise, and the sources of current contributing to the fault on bus 2. At the bottom, there's a summary showing the maximum current for a fault on each bus. PTW can also provide a DC short circuit analysis in accordance with IEC standard 61660. Since we started our example project using ANSI standards, it will be necessary to change the project option for the applicable standard. This is accomplished by going to Project, Options, Application, and changing from ANSI to IEC. Typically, when working in the IEC environment, we would also change our units to metric and their system frequency to 50 Hz. However, for consistency with our previous ANSI study, we'll leave those as they are. When we return to the component editor, we now see that there is an IEC short circuit subview for the battery component. For this example, we will try to provide data that duplicates that used for the ANSI study. There are several options for defining the battery open circuit voltage. For our purposes, we'll use the calculator with a voltage factor of 0.95. Based on the methodology we used in the ANSI study, the battery resistance is 0.005156 ohms. We'll again use 0.004 millihenries for the inductance. This value is dependent on the arrangement of the battery cells and is a typical value. To match the ANSI study, we will use values of 0.0054 ohms and 0.0001 millihenries for the branch resistance and inductance. Next, we need to provide the motor data needed for the IEC short circuit calculation. Again, we will try to match the data used for the ANSI study. We select the DC motor and the IEC short circuit subview. To add the second AC load bus, we simply select the first group and use the component clone function. Our 20 horsepower motor equates to 14.91 kW. The rated current is 159 amps. The rated motor speed is 2500 RPM, and the no-load speed is 2625 RPM. The moment of inertia is for the combination of the motor and the load. The values must be obtained from the equipment manufacturer. Also, be sure to be careful of the units. For our example, we'll use the motor datasheet value of 0.388 kilogram meters squared. Field circuit inductance values are often reported in henries rather than in millihenries. For our example, we will use 39 and 78 henries respectively for the saturated and unsaturated inductance of the field. Note that the field units are millihenries. For our 20 horsepower motor, the field circuit saturated resistance is 67.7 ohms. The armature resistance is 0.0244 ohms, and the armature inductance is 0.49 millihenries. The branch resistance and inductance values are both 0, and we will also accept the default constant speed assumption for faults longer than 1 second. We can now select the IEC short circuit option, the Setup button, and the IEC short circuit tab. The IEC short circuit setup looks the same as the ANSI short circuit setup. The only thing we need to do here is select the faulted bus to be plotted. For consistency, we select DC bus 2. Note that PTW has again displayed DC bus 2 under the short circuit study. To add additional components, we click our right mouse button on short circuit, select components. From source, we can add the battery. From motor, we can add the DC motor. Now all 3 components show up under IEC, just as they did under the ANSI study. We start the analysis by clicking on the Run button. Again, we see the summary of the AC emergency loads. We click OK to continue and close the study message dialog. To plot the study results, we click on the Plot button, enter a new plot name. We'll call this DC2 IEC. Click New. Now we can plot the current at bus 2 and the contributing currents from the battery and the DC motor. Now let's compare the results of the IEC study to the results of the ANSI study. We'll create a new plot. We'll call the plot ANSI IEC. We'll plot the DC bus 2 total current from the IEC study. Then we'll select the ANSI study results and plot the same value. The results are somewhat different because of the different methods of analysis defined by the 2 standards. Before we leave the graphics, note that you can resize the windows for easier viewing. You can also customize the graphics using the plot properties. Here you can change plot styles, axis ranges, fonts, colors, and add grids. Like the ANSI short circuit study, the IEC short circuit study has a tabular report. Make sure that the IEC short circuit option is selected, then click on the Report button. As in the ANSI report, the IEC fault report displays a list of the fault current sources and a table of pre-fault voltage. The second part of the report lists the detailed fault values flowing into each faulted bus. The end of the report displays a summary of the maximum fault on each bus. For effective DC analysis, it is important to understand the process of adding new battery characteristics to the PTW library. To start with, we need data from the manufacturer. Some manufacturers publish characteristic data on their internet websites, but others only provide the data to customers who purchase a battery. For our demonstration, we'll use typical data from the internet. Battery discharge data may be in graphs and/or in tables and applies to a specific cell design. For the definition of a lead-acid battery into the PTW library, we need data in a per-positive plate format. It can be in the form of a discharge curve, like those shown here, as RT curves or as KT curves. Graphical data is usually given on a per-positive plate basis. Tabular data is typically given for a series of specific cell sizes. Thus, to use the tabular data, it is necessary to divide by the number of positive plates to get per-positive plate data. Before we can enter the data into the library, it is usually necessary to carefully tabulate the data from the graphs. Unfortunately, the data is often less than ideal. Here we have shown some typical data transcribed from the available graphs. To get the best possible results from PTW, it is necessary to expand this data by supplementing the graphical data with information from the tabular form or by careful extrapolation. Here we show where the graphical data has been supplemented to extend the load ampere data for some of the voltage values. For this demonstration, we are only using a limited set of data. For better precision with PTW, more closely spaced data points and more voltages should be used. Once the necessary battery data has been collected, we can create a new record in the PTW library. To open the library, select Document, Library, PTW Library. We open the ptw.lib. Expand DC Equipment, click on Lead-Acid Battery, click our right mouse button to select a new entry. Enter the name of the manufacturer, the type of battery, and a description. These three fields are used to identify the battery characteristic in the library. The number of positive plates is for reference and is not used in the computations. The cell voltage required for charging is normally the maximum equalizing voltage specified by the manufacturer. This value is used by the battery sizing calculation to determine the maximum number of battery cells that can be used without exceeding the maximum system voltage. The rated amp hours per positive plate for an 8-hour discharge comes from the manufacturer's data. The initial cell voltage data is very important because it is used to determine the voltage at time 0 in the load flow study. Some manufacturers provide this data as a part of their discharge graph. It is sometimes called the initial voltage line. Next, we need to enter the discharge data from the data we previously tabulated. We start by selecting the format for the available data. In our case, we're using a discharge curve. Next, we enter the available voltage lines in the blocks at the top of the grid. For our demonstration, we're only going to enter data for 3 voltage lines. Next, we enter the load amps and amp hour data points for the first voltage line. If the data is stored in spreadsheet format, you can save time by using copy-paste. It's a good idea to click on the Save icon from time to time, as battery entries are not saved automatically until you exit the library entry. Once a set of data has been saved, we can check it by looking at the discharge curve plot. We add 2 more sets of data points for voltage 1.78 and 1.81 and save again. To complete the library entry, we would need to enter all available data points, but since this is a demonstration, we'll stop here and check the plot again. As expected, we now have 3 lines of our discharge characteristic. There is one more part of the battery characteristic that we need to enter, and that's the temperature correction factor table. We click on the Temperature Correction tab and enter data as obtained from the battery manufacturer or from the IEEE standard 485. We'll next demonstrate the definition of a new nickel-cadmium battery characteristic for the PTW library. To start, we need data from the manufacturer. For our demonstration, we'll use typical data found on the internet. The capacity data for nickel-cadmium batteries is normally provided in tables and applies to a series of cell sizes for a specific design. Typically 4 tables are provided, one each for the final voltage of 1, 105, 1.1, and 1.14 volts per cell. There are exceptions, such as the data for cells designed for high loads, such as engine starting duty. Parts of typical tables for final voltages of 1.0 and 1.05 volts per cell are shown here. Once the manufacturer's data has been obtained, we can start to create a new record in the PTW library. Instead of lead-acid battery, we select nickel-cadmium battery, click the right mouse button to create a new record. We start by entering identification information, including the manufacturer, type, and description of the battery. An individual nickel-cadmium characteristic in PTW provides sizing data for only a single final voltage, and the discharge curve data applies to only a single cell size. Thus, for our example, we have chosen the sizing data for a final voltage of 1 volt per cell and the discharge data for a cell size of 255 ampere hours. As a record of this choice, we have entered the information into the Notes field. Note that we needed to press Ctrl-Enter after cell to force a line return. The entry for the field labeled Cell Voltage Required for Charging should be the highest voltage that will be used for charging while the battery is connected to the system. Depending upon the system design, this may be the maximum float charging voltage or the high rate charging voltage. The values for a particular cell design can usually be found in the technical instructions applicable to the cell design. For our demonstration, we'll use a typical float voltage of 1.42 volts per cell. The data for the initial cell voltage fields can require some research. For our example, we will use 0.01 amps and 1.3 volts for 0.1 based on a typical nickel-cadmium characteristic. For 0.2, we will use the current rating for a 1-second discharge to 1 volts per cell. This value is 1760 amperes to 1 volt. To define the data for the discharge curve, we need to collect the sizing data for a specific cell size. Tabulated here is the data taken from the manufacturer's tables for the 255 ampere hour cell. As is typical, the data includes the discharge currents for various time to 4 different final voltages. To enter the discharge curve data into the library, we start with the data from our spreadsheet for the final voltage of 1.0 volts per cell. Next, we enter the load amps and amp hour data points for the final voltage of 1.0 volts per cell. To enter the discharge curve data into the library, we start with the data from our spreadsheet for the final voltage of 1.0 volts per cell. As noted before, if the data is stored in spreadsheet format, you can save time using copy and paste. Before continuing, we'll click on the Save icon to save the data entry. Once the data has been saved, we can check it by looking at the discharge curve plot. Returning to the NiCad Battery tab, we can continue entering data. We have now added 3 additional sets of data points for final voltages 1.05, 1.1, and 1.14. We can now check the data by looking at the discharge curve. As expected, we now have 4 lines in our discharge characteristic. The next part of the battery characteristic we need to enter is the sizing data. The information to be entered for battery sizing comes directly from the manufacturer's data tables. For our demonstration, we have chosen to enter the sizing data for a final voltage of 1 volt per cell. This is part of the same data that we started with to establish the discharge curve, except we now use the data for a range of cell sizes. For our demonstration, we will enter only a small portion of the cell sizes for this particular cell design. To begin, we click on the Sizing tab. Here we have entered the sizing data directly from the manufacturer's published table. Note that the manufacturers typically publish data with more discharge times than is required for the PTW input grid. The last part of the nickel-cadmium characteristic that we need is the temperature correction factor table. To begin, we click on the Temperature Correction tab. The temperature correction data is specific to each cell design and is normally found in the technical manual published by the manufacturer. The data is usually presented in graphical form, as shown here, and is typically given as derating factors that are less than 1. First, we need to tabulate this data, and then we will perform some calculations in order to obtain the temperature correction factors in the form needed for the entry in the PTW library. Shown here is the result of our effort to carefully record the data from the graphical presentation of the temperature derating factors. Here we have used linear extrapolation to determine derating factors for each of the discharge rates that will be needed for entry into PTW. Note that in addition to extrapolation, we must apply the restriction that the derating factor is always 1.0 or less. As a check on the data tabulation and extrapolation effort, it's a good idea to plot the results as shown here. This can be performed using a simple spreadsheet. Once the extrapolation of the derating factors is complete and checked, the PTW correction factors can be calculated by taking the inverse of the derating factors. The result is shown here with both the derating factors and the correction factors. This was also accomplished using a spreadsheet. We complete the effort by entering the calculated temperature correction factors into the data grid. The resulting data is shown here. Now that we have developed a new nickel-cadmium battery characteristic, we will use it as an alternative source for our sample system. We select our battery component, then select the Library button, expand nickel-cadmium, and select the entry. Now that we've selected a nickel-cadmium battery, we need to make some adjustments to the sizing criteria, so we click on the Sizing tab. The characteristic field does not really apply to the nickel-cadmium characteristic, so no change is required. We will, however, adjust the acceptable maximum and minimum system voltages. Nickel-cadmium batteries are often applied with a much wider voltage range between float charge voltage and the final voltage as compared to lead-acid batteries. Therefore, we will set our maximum system voltage to 142 volts and our minimum system voltage to 100 volts. We are also going to adjust our design margin to 10% and our aging factor to 1.1. To run the battery sizing analysis, we select Run, DC System Analysis, and select Battery Sizing. We click the Run button, accept the emergency loads as displayed, and the battery sizing study is complete. We close the study message dialog and click on the Report button. We can now see a battery sizing report consistent with the worksheet format appropriate for a nickel-cadmium battery. If we scroll to the bottom, we see that we need a battery with a cell type HB255P, which is the 255 amp-hour rated cell. If we return to the component editor, we can see that the battery now needs 100 cells with a minimum voltage per cell of 1 volt. Now that the battery sizing with the NiCad battery is complete, we can rerun our load flow study. We can expand the load flow component selections. Since we are happy with the buses and cables defined for inclusion in the original load flow study, we are ready to run the new study. We click the Setup button to check our load flow study options. We then click Run to run the study. We're again presented with the summary of AC emergency loads and accept them as presented. We close the study message dialog and see our load flow report. We'll create a new plot to view our results graphically. First, we'll look at the voltage on bus 1, which is the battery terminal. The result is a plot of voltage versus time for bus 1. At first glance, the plot looks like there are wide voltage swings, but a check of the voltage scale shows that the voltage swing is not as big as it looks at first glance. During most of the discharge, a NiCad battery provides about 1.2 volts per cell. Thus, with our 100-cell battery, the battery voltage is approximately 120 volts, except for periods of high discharge current. Next, let's look at load current on the battery. We'll turn off the voltage plot and plot the current in DC cable 1. As would be expected from the voltage profile, the load current is high at the beginning of the discharge profile, then drops to a fairly steady value. For more detail, we can return to the report by clicking on the Report button. There are several DC components that were not included in our tutorial. We'll therefore use another sample project to acquaint you with these components, including a rectifier, DC generator, and a DC train load. The rectifier specification includes a rated voltage for the AC side, a rated voltage for the DC side, and a rated kW. The rectifier is also assumed to have a unit transformer that requires specification of primary and secondary rated voltage and impedance expressed in %Z and X/R on a common base. The rectifier load flow subview allows selection of the control mode, including constant voltage, constant current, or constant firing angle, for a fixed time duration. The rectifier short circuit subview allows specification of the rectifier type, rated DC current, internal circuit impedance, and unit transformer impedance. The DC generator specification includes a rated voltage, source type, and source schedule. For this example, we have specified a constant voltage source scheduled for 701 volts for 75 minutes. The DC generator short circuit subview includes entry for rated size, rated speed, and impedance. The train load specification includes rated voltage, total resistance and inductance, which includes the catenary or third rail, and the return path between the two source buses. A variable load and position specification is also defined. In this example, we have specified the load as 100 kW for 10 minutes at 10% along the line, 75 kW for 5 minutes at 20%, 85 kW for 15 minutes at 40%, 80 kW for 15 minutes at 60%, and 85 kW for 15 minutes at 90% along the line. If we look at the load flow results, we see that for a train running between bus 2 and bus 4, that the voltage on bus 2 increases with the progress of the train, while the voltage on bus 4 decreases. The current feeding bus 2 and bus 4 shows more dramatically the effect of the train moving from one source to the other. Note, however, that this plot also includes the current to the motors. This concludes the tutorial on the use of the DC System Analysis module in the SKM Power Tools software. For additional information about the DC Analysis module or any of the SKM Power Tools software, contact SKM Systems Analysis at 1-800-232-6789, visit our website at www.skm.com, or send an email to sales@skm.com.